All right, taking a look at problems 6 and 7. The picture is given in your answer or question sheet, and I'm just going to redraw it here. I know I've got a 20 kilogram block that's sitting on a table. I've got a string going over a pulley to a 10 kilogram block hanging over the side. This is going to be a little bit different than when we had similar drawings in equilibrium, because now the tension is not going to equal the force of gravity here, because one of them has got to be bigger than the other because this whole system is accelerating, meaning for this block in this game of tug of war, gravity is going to be bigger than the tension force. And tension here is got to be bigger than nothing because there's no force of friction. The question says it's a frictionless table. Part A, it says calculate the acceleration of both of the blocks. Block A, which is the block on the table, and block B, which is the one that's hanging here. First thing I need to do is figure out an equation for each block in the direction that it's going to accelerate. For block A, it's going to accelerate to the right. So I'm looking at my left-right arrows. So for block A, what arrows do I have? I have tension, because tension pulls to the right. That's why it's positive. And that's going to equal mass times acceleration for block A. For block B, I've got gravity and I've got tension, but which one do I make positive and which one do I make negative? Here's why we have this little arrow here deciding our positives and negatives. For things that only move one object moving left and right or up and down, it's very easy. When we have two objects tied together, we have to make sure that our directions match up. And here's what that means. For this block on the table, if it goes right, since it's attached to a string, if this block is moving right, this one's going to go down. So if I say that right is positive, then I have to say that down is also positive. Basically, if you just follow the string, I'm saying that particular direction is positive. However, if I grabbed onto block A and I pulled it to the left, this block would go up when this block goes to the left. I'm saying any arrow that points in that direction is negative. So for block B, force of gravity downward is actually a positive force because that's the force that's going to make this block move to the right. So I said force of gravity is positive. Tension goes in the other direction, so it's minus force of tension, and that's going to equal the mass times the acceleration of block B. That's why it says mb for mass B times the acceleration. We have a simultaneous equation because we do not know what the tensions are, and we do not know what the accelerations are. We have two equations and two variables, but this is a really easy simultaneous equation. If I add these two equations together, so I add up all the terms on the left side of the equal signs, and I add up both of the terms on the right side of the equal signs, here's what happens. If I set it up properly, my tensions will always cancel. I have a positive tension minus tension just equals 0. That's why I have little lines through them. They go away. So on the left side, the only force that remains is force of gravity. So that's it. On the right side, I have to add mass of block A times acceleration and mass of block B times acceleration, which is why I have mass of block A acceleration plus mass of block B acceleration right here. Now I'm trying to solve for the acceleration. By the way, the physics is over at this point. We're just doing algebra. So I'm going to factor my A out because it's in both terms. So now my acceleration's on the outside and my masses are in parentheses. And to finish up solving for A, divide by both of the masses. That's why they're both in the denominator over here. So the force of gravity acting on this block is mass times 9.8. So that's 10 kilograms times 9.8 because we're talking about the hanging block. The two masses put together in here in the bottom are 20 and 10. So that would be 30 kilograms in the bottom. And when I do a little bit of division, I get 3.27 meters per second squared for the acceleration of the system. Part B says, well, what's the tension in the rope? Because if we were going to set something like this up, maybe we want to make sure we have a rope that can hold both of these things so that it doesn't snap. How would I do that? Well, I can take a look at either of my first two equations that I came up with for block A or block B. I now know what acceleration is. I know what the masses are. I can solve for tension. So I just take the equation for block A, which was tension equals mass times acceleration, plug in the mass, which is 20, plug in the acceleration of 3.27 meters per second squared, and I know that the tension has to be 65.4 newtons. That's the end of number 6. For number 7, it's a very similar problem, but it's worded a little bit more fun with a young couple passing time in a car. I'm sure they're just talking, playing Scrabble or something. And they're 10 meters away from the edge of the cliff. The car's mass, including the people, is 1,000 kilograms, written on the problem. And some jealous guy decides that he's going to drop a 75 kilogram rock tied to a rope to the car. We want to know A, first, what does the picture look like so that we have all the forces? B, what is the acceleration of the car as it moves now towards the edge of the cliff? And C, how long do they have to apply the brakes before they go over the edge? We know that the force of friction for everything is 35 newtons because that was given in the problem. So part A, here's my picture. Normal goes up, gravity down, friction goes to the left, tension is pulling the car to the right. For the hanging rock, tension goes up, gravity goes down. This setup is almost identical to number 6 because I'm going to have two equations, one for the car, one for the rock. So for the car, tension is going to the right, friction is going to the left, and I'm saying anything to the right and for the hanging block down is positive. So tension is positive, and friction, because it goes to the left, is negative. That's going to equal the mass of the car times the acceleration of the car. For the rock, force of gravity goes in the positive direction. Tension is going in the negative direction, so gravity minus tension equals the mass of the rock times the acceleration. We're going to add the equations together just like we did in number 6, and what's going to happen is my two tensions cancel because one is positive and the other one is negative, so they disappear, leaving me with force of gravity, positive, and force of friction, which is minus, so we keep it negative, adds up to equal the mass times the acceleration of both objects. Again, we factor out the acceleration to get it by itself and divide by the masses. That's why it's in the denominator here. Now I can plug in some numbers. Mass of the hanging rock, 75 kilograms times 9.8 meters per second squared, minus the force of friction, given in the problem to be 35 newtons, all divided by the two masses put together, which is 1,075 kilograms, tells me that it's going to accelerate 0.65 meters per second squared toward the edge of the cliff. Part C says, well, how long do they have to hit the brakes before they're going to go over the edge? Well, they're 10 meters away from the edge of the cliff. The initial speed of the car is 0. That was given. And the acceleration we just solved for is 0.65 meters per second squared, and we are solving for time. So I'm going to use the equation that does not have VF in it. So that's going to be the D equals V naught T plus 1/2 AT squared. It's normally a quadratic, but since V naught is 0, it cancels, leaving me with just D equals 1/2 AT squared. I move my 1/2 over by multiplying by 2. That's why I have a 2 times D. I divide by the acceleration. And in order to get rid of that little squared, I have to do the square root. Plug in my numbers, 2 times 10 meters, divided by 0.65 meters per second squared. Take the square root, and they have a little over 5.5 seconds to hit the brakes. Otherwise, they're not going to have a very good night.